In our previous section, we looked at how many ways we can combine items from different groups. In this section, 11.2, we're going to be looking at permutations. A permutation looks at how many ways we can arrange items in the same group. So for each permutation, we're going to look at one group. So one permutation, one group. The order matters because what we're doing in a permutation is we're looking at how many ways we can arrange the items in the group. And we can't use an item more than once. Example 1, in how many different ways can you arrange 5 shirts in your closet? So notice that we have a total of 5 shirts. This is one group. All we're doing is saying how many different ways we can arrange these 5 shirts in our closet. So I'm going to make some lines for the first shirt, second shirt, third, fourth, and fifth. So remember, the order matters in a permutation, and you can only use an item more than once. It doesn't make sense that you're going to take one shirt and use it 10 times because you've only got one of them. So I have 5 shirts. When I pick which shirt's going to go first, I have 5 choices. But think about this. I've chosen one of those shirts to be first in my closet. Now when I choose the second shirt, I only have 4 shirts left to choose from because I can't use a shirt more than once. When I choose the third shirt in the closet, I now only have 3 shirts left, and so on. So we just multiply all of these together, 5 times 4 times 3 times 2 times 1, and that will give us 120. So there's 120 ways that you can arrange 5 shirts in your closet. Let's look at another example. Example 2, based on their long-standing contribution to rock music, you decide that the Rolling Stones should be the last group to perform at a 4-group U2, Springsteen, Aerosmith, Rolling Stones concert. So if U2 is to be the opening act, in how many ways can you put together the concert? Okay, so as I read through this, I see that I have 4 groups, okay? Or 4 performances. So order matters here in the concert. 1, 2, 3, 4. This is a permutation where I'm taking these 4 groups and I'm looking at how many ways I can rearrange them so I can make a schedule. However, I have some conditions. The Rolling Stones should be the last group. So when you think about who's going to perform first, second, third, and fourth, which would be last, I only have one choice for who's going to play last because that's the Rolling Stones. All right, and I also have another condition. U2 is the opening act. So when I think about who's going to perform first, I only have one choice. Remember, what I'm writing down is the amount of choices I have. That has to be U2. I can't use a group more than once. So when I think about who's going to play second, I can only choose Springsteen or Aerosmith. So I only have 2 choices for who's going to go second. Once I've chosen who's going to perform second, now I only have one group left. Oop. So multiply these all out, and we get 2. There are 2 ways to schedule it so that the Rolling Stone goes last, U2 goes first. This is going to bring us to a factorial. So if you're not familiar with a factorial is a multiplication or a product where you start with the largest positive integer and then you multiply by subtracting 1. until you are at the number 1. The notation that we use for the factorial is the exclamation point. So if you see an exclamation point after a number, you know it's a factorial. I'm going to go back up to our first example. Notice that this is 5, 4, 3, 2, 1, which is simply a factorial. We always write it with the highest number because that's where we start at 5. And then we put our exclamation point. So your calculator that you're using may have this exclamation point on it, and that means it's a factorial. So in your calculator, if you're going to figure out a factorial, you would put the number in, choose the factorial key, and then press enter. It should give you 120. In example 2, since the Rolling Stones and U2, they had a specific position, I was not rearranging them. Their position is set. The only thing I really had to figure out how to rearrange were the remaining 2 groups. So that's actually 2 factorial, which is 2 times 1, or 2. Okay, so let's look at some examples of factorials. If you have 1 factorial, that's simply 1. 2 factorial, 2 times 1, which is 2. 3 factorial, 3 times 2 times 1, which is 6. 4 factorial, 4, 3, 2, 1, it's 24. 5 factorial is 5, 4, 3, 2, 1, which is 120. Okay, so now I'm going to go to 6 factorial. I could write 6 times 5 times 4 times 3 times 2 times 1, but let me just show you something. 6 factorial is the same as 6 times 5, 4, 3, 2, 1. But 5, 4, 3, 2, 1 is simply 5 factorial. So I don't have to do the whole product. All I have to do is take 6 times 5 factorial, which was 120. I already figured out 5 factorial in the previous step, so there's no sense in me doing it twice. So when I looked at 7 factorial, that's 7 times 6, 5, 4, 3, 2, 1, which is 6 factorial. So I can take 7 times 6 factorial was 720, which would give me 5,040. In this box is the formula for factorial. So if you have n, which is a positive integer, can't be negative, n exclamation or n factorial is going to be product of all positive integers from n to 1. So we always start out with n times, subtract 1, and you have n minus 1 would be the next number. Subtract 2 from n, and you get n minus 2, and so on until you get down to 2 times 1. So here's something that's important. Whenever you look at 0 factorial, it's not 0. 0 factorial is defined as equaling 1. And we'll look at an example where we have to use a 0 factorial. But first, let's go ahead and practice using factorials by hand. Remember, you can use a calculator if you have the factorial key. 9 factorial over 7 factorial. I'm going to write this out as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And I never have to write the 1, right? Because this is a multiplication. 1's not going to change it. Now I'm going to do 7 factorial, but I'm going to kind of write the 7 factorial so that the factors match in the numerator and denominator. That's 7, 6, 5, 4, 3, 2, 1. So if you're figuring out factorials by hand, remember that when you have a product in the numerator and denominator and you have the same factor in the numerator and denominator, you can just cancel them. So the 3's cancel, 4's, 5's, 6, and 7. So 9 factorial over 7 factorial is simply 9 times 8, which is 72. Let me go ahead and write this in a different way. Notice, and again, I'm just doing this by hand. If you have a calculator, you don't have to do this. Notice that the 9 is bigger than the 7. So 9 factorial is 9 times 8 times 7, 6, 5, 4, 3, 2, 1, which is 7 factorial. So since I know there's a 7 factorial in the denominator, I'm going to just write 9 times 8 times and keep it as 7 factorial because I can see that the 7 factorial will cancel. Remember, this is just a number. Same number, top and bottom, cancels. And you still get 72. If you're doing these by hand, there's a lot of little tricks. Look at part B, 100 factorial over 99 factorial. I can tell you right now that's 100. I'm not going to go 100, 99, 98, 97 and expand it all out. That's just crazy. But I do know that this is 100 times 99 factorial over 99 factorial, and I know that those will cancel. So the answer is simply 100. We do have to be careful though. Factorials do not distribute over addition or subtraction. So if I have in parentheses 6 minus 3 factorial, I have to do the 6 minus 3 first and follow my order of operations and write that as 3 factorial over 3 factorial. And now 3 factorial over 3 factorial is simply 1. Look at part D. What if you did distribute the factorial? Well, part D, if you could distribute the factorial over subtraction, then C and D should give me the same answer, but they don't. Notice there's no parentheses, so the order of operation is I have to do the 6 factorial first, which would be my 6 times 5 times 4 times 3 times 2 times 1. I'll write it out even though I don't have to. I could simply put in 720. So that is my 6 factorial, and I'm going to subtract the 3 factorial, which is 3 times 2 times 1, all over 3 factorial, which is 3 times 2 times 1. Notice that I cannot cancel the 3, 2, 1 top and bottom because of this subtraction. You can only cancel if everything is multiplication. So I have to figure out each piece separately. The 6 factorial is 720 minus the 3 factorial is 6 over 6. Again, I have to do this separately. I cannot cancel that 6 because of the subtraction. So just remember your algebra. This is going to be 714 over 6. And now we never leave fractions not reduced. We always reduce them. So 6 goes into 714. 1, 9. So 119. Again, feel free to use calculator. In fact, you should be using a calculator for all of this. We're in the section of permutations. It makes sense that we're going to have a permutation formula. Then this next example, I'm going to show you where the permutation formula comes from. You don't have to memorize this. And in fact, since this is an open book course, you really don't have to memorize anything, but you should know how to use the permutation formula. Example 4, you're a coach on a Little League baseball team. There are 13 players on the team. You need to make a batting order using 9 players. Of course, the order matters in a batting order. So how many batting orders can you make? Okay, so I have a group of 13 players. So my group is my team. However, I'm not looking at how many ways I can rearrange those 13 players. When I'm making my batting order, I can only choose 9 of the players for my batting order. So I'm not rearranging the whole team. So let's look at how many choices I have for the first batter. So for the first batter, since I have 13 players, I have 13 choices. And let's say that I chose my first batter. When I choose my second batter, I now only have 12 choices because I've already chosen one of those players. I can't use them again. And then for the third, it's one less, so it's 11, 10, 9, 8, 7, 6, and 5. I'm not going all the way to 4, 3, 2, 1 because I'm only choosing 9 out of 13. And when I put this in my calculator, when I multiply this all out, I get 2,059,459. Oh my gosh, 259,459,200 ways that I could make my batting order. And here we're only choosing 9 out of our 13 players. With this example, I'm going to go ahead and create our permutation formula. So remember, this is what I had. 13, ooh, don't want the thick one, I want the thin one. 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5. Okay, so I could write that as a fraction. Now, what if I was to take this fraction and multiply the top and the bottom by 4 factorial? So what if I was to multiply the top and the bottom each by 4 times 3 times 2 times 1? Then notice that these two are still equal, aren't they? Because the 4, 3, 2, 1 will cancel and back to where I started from. Now look at the numerator. It's 13 factorial. And in the denominator, I have 4 factorial. So remember, there were 13 players on the team. But the 4 factorial means nothing to me because I actually chose 9 out of the 13 players. But what is 13 minus 9? 13 minus 9 is 4. So this is our permutation formula. We're going to let the total number of items in our group be n. In our case, n is 13. The number that we're choosing is going to be r in the formula. So we're choosing 9, so r is 9. So this becomes 13 or n factorial over, in parentheses, the total was n, minus the amount I was choosing was 9, so that's my r, parentheses factorial. And that's our permutation formula. So the permutation of n things total, taken r at a time, is this formula here. Now, if you're using a calculator that has this NPR, awesome. You should be using that calculator. So what you would do is you would put the total number of items, your n, in first in your calculator, choose the NPR key, and then enter in the number of R items, and then equal. In example 5, we're going to use this permutation formula. Let's say we have a corporation with 7 members. So my group is this 7 members in this corporation on the board of the directors. How many ways can we elect a president, a vice president, a secretary, and a treasurer? Now here, this is a permutation. We have one group, our board of directors, with 7 members. Order matters. It matters who you choose as president, vice president, secretary, and treasurer. And you could just look at our government. It would be a different administration if Pence was president, Trump was vice president, or maybe not. So since the order matters, and I'm choosing from one group, and I can't use somebody more than once, this is an example of a permutation. But here, I have 7 total members, so n is 7. And I'm choosing a president, vice president, secretary, and treasurer. So there's 4 positions, so my R is 4. And then I would use a permutation formula. It's always n first, so it's 7p4. If you're putting this in your calculator, you should have already gotten 840. If you're putting this in a calculator. If you're not, then 7p4 is the same as 7 factorial over 7 minus 4 in parentheses factorial, which would be 7 factorial over 3 factorial. And 7 factorial is 7 times 6 times 5 times 4 times 321 is 3 factorial, so I'm just going to write 3 factorial over 3 factorial, and those cancel. So 7 times 6 times 5 times 4 should be 840. And one more example. Let's say there's 50 runners in a race. So in how many ways can you award a first, second, and a third place? So we have the one group, the 50 runners. That would be my N. And I'm awarding a first, second, and third place. So since I'm giving out 3 awards, my R is 3. And now the amount of ways is the permutation 50p3. Okay, so again, if you have a calculator, use it. You'll get 117600. Otherwise, you could figure this out by hand. It's 50 factorial over 50 is your N minus your R, which was 3, in parentheses factorial. So 50 minus 3, that's going to be 47. And then that would be 50 times 49 times 48 times, and then the 47 factorials will cancel. And you'll end up with the same answer, 117600. So before we go any further, what I'd like to do is recall our first example. So this has nothing to do with what we just did. Remember in the first couple examples, we hadn't even talked about the permutation formula. Well, let's go back to the 5 shirts in a closet. So that was 5 shirts. And we were going to see how many different ways we could rearrange them. Notice that I can use the permutation formula. I have a total N, oops, why do I constantly do that? I have a total N, which is 5, the total number of shirts. How many shirts am I choosing? I'm choosing all 5. So my permutation formula would be 5p5. 5 factorial over parentheses N, which is 5, minus R, which is 5. And that's why we need, that's why we need our 0 factorial to be 1. Because this would be 5 factorial over 0 factorial. Now, a lot of people want to write 0 factorial as 0. But it's not a positive integer, so it doesn't follow the formula. We just have to know that 0 factorial is 1. Because if you did write 0, you can't divide by 0. So mathematically, we would be stuck. This is 5 factorial over 1, which is simply 5 factorial. And that would give us the 120 that we had previously when we did that example. the last formula we're going to talk about in permutations, remember we're working with one group and we're looking at how we can arrange the items in the group. The last thing we want to talk about is what we call a permutation of duplicate items. So it could happen that you have a group where you have a duplication or items that are the same. For example, let's say I have the word set, S-E-T, and I look at the three letters, S-E-T, and let's say that's my group. Well, all these letters are different. None of them are duplicates. So to figure out all the numbers of permutations, all the different arrangements, it'll turn out to be 3 factorial or 6. So I have SET, STE, EST, ETS, TES, and TSE. Those are all the different ways I can rearrange those 3 different letters. And that would be 6. Let's look at Anna. Problem with Anna is that in this group I have duplicate items. I have 2 A's. So let's look at the first arrangement. I'm going to look at the first A as being red and the second A as being green. If I were to swap the A's, this would still be ANA. So it's one permutation. If I were to put the 2 A's first and then change their order, I have one permutation. Let's say I put the 2 A's last and then switch their order. Again, same permutation. So really, I only have 3 distinct permutations because 2 of my letters were identical. They were duplicates, which brings us to the permutation formula for duplicate items. Let's say we have n items. And let's say we have identical or duplicate items. We'll call these PQR. Then the permutation formula, when you're trying to figure out how to arrange all the items in a group with duplicate items, would be n factorial over p factorial, q factorial, r factorial, and so on, depending on how many items duplicate. Oftentimes when you see formulas, it's a little bit difficult to use, so let's look at an example instead. Example 7, in how many distinct ways can the digits of the number 2550888 be arranged? So all those digits, that's my group. Notice that I have 1, 2, 3, 4, 5, 6, 7. My n is equal to 7. However, some of the items duplicate. And I only have to list the ones that duplicate. So notice that the number 2, I only have one of those. So I'm not going to bother to write that. The 5, I have 2 of them. So when I look at the number 5, I'm going to let that be the P in the formula. P, Q, R, those are numbers. Remember, we're putting numbers. All these letters stand for numbers in the formula. So P is the number of 5s I have. And since I have 2 5s, P is 2. If I look at 0, there's only 1, so I don't have to list it. But look at 8. I have 1, 2, 3 8s. So when I look at the number 8, that's going to be in the formula my Q. So how many 8s do I have? 3. So Q is 3. So the number of ways that I could arrange these digits would be the total 7 factorial over the 5, I have 2 of them, so that's 2 factorial. The 8, I have 3 of those, so that's 3 factorial. I don't have to list the number 2 or the number 0 since there's only 1. I could write, okay, well, there's only 1 2, so I could put in a 1 factorial. And there's only 1 0, so I could put in a 1 factorial. But 1 factorial is simply 1. And multiplication by 1 doesn't change anything, which is why you only have to put in the ones that duplicate. So I could do this by hand, or I could use a calculator. If I were to do this by hand, I would probably go 7, 6, 5, 4, and in the denominator I see the 3 factorial is the largest factorial. So I'll do 2 factorial is 2 times 1, and then times 3 factorial. And I can cancel the 3 factorial. I can cancel the 1. So I just have 7, 6, 5, 4 over 2. And in fact, I can even reduce by 2 if I want. So 7 times 6 times 5 times 2 should be 420. Last example using this formula. So in how many distinct ways can the letters of the word Ko'olaupoku be arranged? So let's count up all those letters. It looks like I have 3, 6, 9, 10. So N is 10. Now the K, I have 1, 2 of them. So my formula is going to be the total 10 factorial over K is 2, so I have 2 factorial. O, 1, 2, 3, 4 O's, so 4 factorial. L, there's only one, I don't have to list it. A, only one, I don't have to list it. U, only one, don't have to list it. And P, only one, I don't have to list it. So this is 10 factorial over everything that duplicates, so 2 factorial times 4 factorial. I can go 10 times 9 times 8 times 7 times 6 times 5 times, I see a 4 factorial. Again, you don't have to do this by hand. The 2 factorial is 2 times 1 times, and I'm going to keep the 4 factorial because it cancels. So does the 1. So I never really have to write that. And then I can divide the top and bottom by 2 if I wish. Maybe I'll divide the 6 by 2. And then multiplying all this out, 10 times 9 times 8 times 7 times 3 times 5 is 7, 5, 6, 0, 0. I believe in my calculator, but double check me on that. And that's it for this section. In the next section, we're going to be looking at our last way that we range or count items. So 11, 1, 11, 2, 11, 3 is just different ways that we can count things. And then the remainder of this chapter will be computing different types of probabilities. So we haven't even started to talk about probabilities yet. Okay, so that's it for this section.